Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 6, Part 2, and video number 17. So in this video, we're going to continue talking about unbiased estimators, and in fact, we're going to look at an example where we prove that the expected value of the sample variance, S squared, is equal to sigma squared. So it's an unbiased estimator. Why don't we go ahead and get started? All right, so this is example 6. So we want to let x1 to x2 up to xn be IID with a PDF or PMF f of x. Then the population mean and variance are given by these formulas, which we should definitely know here. For we're going to assume that this is PDF in this case. But we know how to do this if it's discrete. We have to use summations instead of integrals, right? So this holds for the continuous case, and it'll be a little easier for us to, or it may be a little easier for us to see. Okay, so we know that. We showed in Chapter 5 that the expected value of x bar is equal to mu, so in general, x bar is an unbiased estimator of mu, okay? Now we're going to take on a little more complicated example. So let S squared equal the sample variance. So that's the sum of xi minus x bar quantity squared divided by n minus 1. And our claim is that S squared is an unbiased estimator of sigma squared. So the proof, to start the proof, we're going to multiply both sides of this equation by n minus 1, and that leaves us just the summation to work with. So now we're going to do a trick. So this is equal to xi minus mu plus mu minus x bar, all quantity squared. So now what we're going to do is we're going to group. We're going to group within the summation. So I'm going to use a bracket here. And then we'll have xi minus mu plus mu minus x bar, quantity squared. Okay, so that's how we start. Now, that's just grouping, but if you know how the proof is going to end, then you know that what you need to do here is to reverse the signs in here. So we need to factor out a negative, okay? And that will make this solution a lot easier. So I'm not going to pretend that you can just see this from here. It's by working through this and then realizing, hey, what we need to do is we need to reverse the order of these two, and then this solves. And you can do that. So, and it's a lot neater if we do it now. So we're going to do xi minus mu, and then we're going to say minus, and so the signs inside the parentheses reverse, so we have x bar minus mu, quantity squared. Now we're going to expand the square. One of the few times that we do that is with these summations. So it's going to be xi minus mu quantity squared minus 2 times xi minus mu times x bar minus mu plus x bar minus mu quantity squared. Okay? Now we're going to distribute the summation. We don't have a square over the whole thing anymore. We can distribute the summation. It is a linear operator. So this is equal to the sum of xi minus mu quantity squared minus 2. Now x bar minus mu doesn't have any subscript I to it, so that can come to the front of the summation. So can the 2. So I'm going to have 2 x bar minus mu summation xi minus mu plus the sum of x bar minus mu quantity squared. Okay. Now, so what we're going to do now is we're going to look at this term here. And we see that there are, again, no subscripts, so this is I equals 1 to n. So we're going to add this n times to itself. And so that's going to become n of x bar minus mu. That's what this quantity becomes. Okay, and we're going to distribute this summation across here. Okay. Okay. So let's do that. So now we have equals the sum of xi minus mu quantity squared minus 2x bar minus mu times the sum of xi minus the sum of mu. And the sum of mu is going to again be n mu. Mu doesn't have any subscripts here, so we have mu plus mu n times. There's n of these, so that is by definition n times mu. Okay, so this is something you need to know so that you can do these derivations yourself. All right, so we have that, and then we have plus n times x bar minus mu squared. Okay, so it stays squared here. Okay, and this is equal to, see if we can squeeze this in here, the sum of xi minus mu quantity squared minus 2 times x bar minus mu. And now we're going to use a trick that we've used before. This is the same as n over n sum of xi, which is equal to n times sum of xi over n, which is equal to n times x bar. Okay, so we're going to exchange this with this. Okay, we're going to substitute. So this is going to be nx bar minus n mu, because we said n mu here, and then plus n x bar minus mu quantity squared. Okay, so I'm going to get rid of as much of this as I can. I'm going to have to come over and, okay. There we go. And then I'm going to get rid of this. All right, clean up our proof here. Okay, so now this is equal to, and we have the sum of xi minus mu quantity squared. Now we have minus 2, and I can factor out an n from both of these. And so I pull an n out here. That's going to leave this as x bar minus mu. I have another x bar minus mu here. And so this is going to be 2n x bar minus mu squared. And then don't forget this term that I had to write up here, plus n x bar minus mu quantity squared. So I will get rid of this. And okay, so now we can see that, oops, still on the eraser. So we have negative 2n x bar minus mu squared plus n x bar minus mu squared. So we can simplify this to sum of xi minus mu quantity squared minus n times x bar minus mu squared. Okay. Okay, so now we have it to a point to where we can take the expectation. So remember that this quantity here is equal to what we started with up here, which is n minus 1 times s squared. So this is equal to e of n minus 1 times s squared. Or, I'm sorry, not e. This is just equal to, let's reverse this now. N minus 1 S squared. I was getting ahead of myself. The next thing we're going to do, so this is what we ended up with. So we're going to take the expectation of both sides. I'm going to put this one first. So we're going to have E of n minus 1 times S squared is equal to E of the sum of xi minus mu quantity squared minus n x bar minus mu quantity squared. So the expectation of that. All right. Remember that the expectation is a linear operator, so I can think about this as distributing it across the addition or subtraction. So this becomes E of the sum of xi minus mu quantity squared minus n E of x bar minus mu quantity squared. Okay, so that's this one. And so now we have two terms. So again, I can take the expectation of the sum as the sum of the expectations. I can distribute this inside the summation sign. Okay, and I should know what this is equal to. Okay, so these are constants. So, I can look at this and remember that the variance of x is equal to E of x minus mu squared. So this is E of x bar minus mu squared, so this has to be the variance of x bar, okay, for this. So this is n variance of x bar here, okay? So equals to, or I can put that above, equals to, now I have the sum of E of xi minus mu quantity squared minus n variance of x bar. Okay? So now this is the variance of xi, which they're IID, so that's going to be sigma squared, minus n variance of x bar. Okay. So remember that this is going to be n times sigma squared, and then minus n, and the variance of x bar is sigma squared over n. Okay? So this is going to be n sigma squared minus sigma squared. And now I factor out sigma squared, and I get n minus 1. So this is equal to n minus 1 sigma squared, and that is E of this. So therefore, E of S squared, okay, so E, so when I rewrite this, let me do this fully, every step. So I've got E of n minus 1 S squared equals n minus 1 E of S squared. And so this quantity is equal to this quantity. So these cancel out, and this leaves E of S squared is equal to sigma squared. And there is our proof. So therefore, S squared is an unbiased estimator of sigma squared. Okay, I guess I should put the n there, not here. Okay, we have proved what we set out to prove. Okay, so here's the conclusion that you need to put on your formula sheets. S squared equals the sample variance is this formula, you should have that, and it's an unbiased estimator of sigma squared. So you could put E of S squared equals sigma squared if you know what that means, or you could put that it's an unbiased estimator. You may want to put both and say IE or that. The MLE of sigma squared is sigma hat squared, which is 1 over n sum of xi minus x bar. This is a biased estimator. However, I can substitute in, I can write this expression in terms of s squared. How do I do that? Remember that this term here, this is n minus 1 times s squared. We showed that. So substitute this in for this quantity, and we get n minus 1 over n times s squared. Now, as n approaches infinity, n minus 1 over n approaches 1. So as the sample size gets larger, sigma hat squared, the MLE, approaches, I shouldn't have s squared here, sorry, approaches sigma squared. Okay? So we say that sigma hat squared, the MLE, is asymptotically unbiased. It is biased, but asymptotically it's unbiased. Okay, so I think that's enough for this video. We'll continue with the method of moments in the next video. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.